Okay, now I'm gonna cover the slit experiment, and the slit experiment I think is yeah, I think it was Richard Feynman. He said, you know, slit experiment is what defines quantum mechanics, because that's the one that drove them nuts. They said, how does Mother Nature do this? And they couldn't figure it out. And they said, look, you know, sometimes light behaves as a particle, sometimes as a wave. For some experiments we have to use the wave, and for others we have to use the particle. And so they ended up with a political agreement. They said, look, all you wave theorists come over here, all the particle physicists come over here, let's kiss and make up, and let's just call it a wave particle or a wave packet or whatever. And so they kissed, they made up, and they never fought again. And everybody's happy to this day because they don't do physics. Again, it's like Max Born says, it's become more and more abstract. Okay? So what do we have here? Well, double slit, the physical interpretation. I'm going to give you a physical interpretation for the slit experiment. Okay, so what is a slit experiment? Well, we have Mr. Francesco Grimaldi, 1665, and he wrote in his Physico Mathesiis de Lumine. And he said, look, you know, when I run light through two tiny slits, I produce these fringes on the wall. And he says, that's so strange because, you know, I can't understand how this works. We come to 1801, Thomas Young, and specifically he ran an experiment in which he reproduced Grimaldi's results. But more importantly, he reproduced an experiment done by Newton. Newton had read of Grimaldi's accomplishments. And he went in there and he took one of his hairs. I think it was one of his hairs. He did a hair experiment. He pulled his hair out and he said, let's see, what does it do with the hair? Because Grimaldi had done it with two slits. He ran light through two slits. He produced the interference fringes on the wall. And he says, what if I put a hair? What would happen then? So Newton did it with a hair, and he produced fringes as well. And so Thomas Young comes 200 years later, 150, and he says, I'm going to try this. Let's see what happens. He did it with a hair, and he also did it with a wire. And this is his third experiment. And he did it with a human hair. And he measured the width of the hair. He made all these calculations. He said, yeah, effectively, you know, you can produce this effect, this so-called slit experiment, with a hair. Somehow that got buried in history until Bill Gaede dug it back up again, because nobody's done it with a hair, which is much easier to do with a hair than it is to do with two slits. You got to get those slits not only very finely cut, they have to be very thin, but you have to have them very close together. Thomas Young tried to do, he says, I'm going to try to do the same experiment Newton did. And he said he also reproduced fringes on the wall. And in order for you to understand that, you know, if you have a single slit, and you run light through it, it's like shining light through, you know, maybe the keyhole. You know, light shines in there and just opens up and illuminates whatever the wall, whatever's out there, right? It just kind of opens up. And that's what you see with a single slit. But you can't do that with like a needle or a hair or a wire, because the light is blocked by the wire. So now you can't have that same situation. So it's a little different. It's like, is the glass half full or half empty? You know, that kind of situation. Is it the same thing to run light through a slit than it is to run it, you know, against a needle or a wire or a hair and have light go around it? Okay? And that's what we're looking at, that comparison. Okay, so I decided to repeat Mr. Young's experiment, and I did it with a hair. I did it with a needle. So here you can see on the left-hand side, you'll see the needle stuck to a cork. I shine a laser pointer at it. You can see the laser hitting the needle on the right-hand side, and at the far end of the wall, you can see that there's a light. You see that there, right? When you walk all the way up there, you see it. That's what you will find. You will find interference fringes. You see all these fringes extending out from the center point. And that's what we have to explain. How does Mother Nature produce that effect? Okay? And so how do they explain it? Well, here's the way we explain it today. They say, well, imagine that light is made of particles, okay? The particles go out and hit the side of the window, of the slit, and they bounce inwards, and they interfere with the other ball that's hitting the other frame, you know, they meet somewhere in the screen, and where they meet with the same frequency, with the same phase, they have a bright band. And when they don't meet, you know, when they're out of phase, well, they have a dark band. That's how it's explained today. But what if we replace that double slit with a needle? In other words, what if we take the piece on the top and the piece on the bottom and just leave the center point, and you produce interference fringes anyways? That ball would have nothing against which to bounce. That's the problem. And here it is. Let's remove them. I'm going to remove them. 1 and 2. I remove them. Now what is it going to bounce against? See the problem? The problem is the light should go straight forward. It should never hit anything. There's no bouncing. And so now we have a problem, because now we can't explain with particles. Why is this important? Because we had Mr. Albert Einstein and Mr. Niels Bohr, and they debated in 1927 at the 5th Solvay Conference, and they debated for hours, just what I showed a minute ago. They said, oh yeah, we can just run the ball against the frame of the slit and it bounces inwards. Very simple, right? And it turns out that you can't do that with a needle, or what I call the needle experiment. You can call it the wire experiment, Newton's hair experiment, whatever you want to call it. If you put a hair there, then it's got nothing to bounce against, okay? And there it is. We remove it, and it's got nothing to bounce against. So now we have a problem, because we can't do it with particles, and I'm going to show in a second that we can't do it also with waves, okay? So let's see if we can do it now with waves. Well, again, we have the same problem. Why? Because a wave is a one-directional, mechanism. Wave comes out of the atom and should go straight, just like a particle. So what do? Why does the wave come inwards? Well, this is the explanation that you get. The wave, when it hits something, it kind of turns into a particle. Okay, it collapses, the wave function collapses into a particle. Whatever that means to you, that's what it does, okay? But what's the point? The point is that they explain this with waves, with water waves. They say, look, if you want to understand this, it's very easy. Just imagine water going through a little slit, and it'll open up. And if it hits water coming from another slit, well, they'll interfere with each other because water goes outwards. See, here we have 2 slits, slit 1 and slit 2. Okay? If you throw 2 stones in the pond, these ripples will expand, and the ripples from this guy will interfere with the ripples of that guy. That's what that blue image is showing. And what you see at the end are the interference fringes. You can see light, in this case red, red, black, red, black, red, black. What is the problem? With a single slit, water goes out of the slit. It just goes outwards. This is for water, okay? And here you see they've done it with a single slit. This is water. This is an actual picture of a water tank that is vibrating. So the water comes up, and as you can see, it just goes outwards. Here you see another one. The bottom one is dynamic. And they widen the slit. And you can see it just produces different kinds of waves, but they're always outward going. They never interfere with each other. So what is the problem? The problem is that they do it with waves. That's the problem, as I see it. There is no such physical object as a wave. A wave is a concept. It's just something in motion, something that vibrates, whatever a wave is. And this is the typical pictorial representation of a wave. The top one is a dynamic version. The bottom one is a static version. Essentially, a wave, or the electromagnetic wave, is made out of 2 fields. One is the electric field, the other one is the magnetic field. We get that from Mr. Maxwell. They move forward, they only move in one direction. This is one of the problems with it. Okay, this is what they say light is. And this does not actually behave very much like water, because water does not really behave exactly like what they're saying light does, or a transverse wave does, okay? So keep that in mind. Okay, so here we're saying that what they've been looking at all these years is a rope. Rope that interconnects any 2 atoms in the universe. And you can see they're very similar. It's the famous wave that they always give you as a pictorial representation is nothing more than a cross-section of a rope. That's essentially what a wave is. There are differences. The electromagnetic rope is structurally wavy, whereas the electromagnetic wave is a dynamically generated wavy thing. A rope is taut, so it's stretched straight. It's like if you have a highway. It's straight, Cars can only go straight along that highway because the highway is straight. The question is, why would the wave, the electromagnetic wave, be straight? You know, why doesn't it just wiggle and go around? And it doesn't. It's supposed to go straight, because if you shine a light on a mirror or whatever, you see that it's completely straight. You can verify that for yourself. It does travel in a straight line. And you're saying, well, if it's a wave, it's something coming out of the atom, why doesn't it just wiggle and go anywhere it wants? Why does it go exactly straight? The torsionals can only travel rectilinearly along, a rope, so on. You can show this at your home with your grandmother's clothesline. Just move one of the clothespins, and you'll see how the whole rope, if it's pulled tight, the whole signal, the torsion signal, will go straight. It can't go any other way because it's a torsion of the rope. Okay, and here you have again the problem with the wave. It's one wave, whereas the rope is bidirectional. When you move a rope around, really both ends are being affected because it's tied at the other end. Here, if the electromagnetic wave is generated by an atom, it can only go in one direction, just like a particle. It's just that you're replacing the particle with a wave. That's why they have made it into a wave packet, because it was kind of handy, comfortable, and so on. Okay, and what is the problem? Well, one of the problems is this C equals frequency times wavelength equation. Okay, and you don't have to be a rocket scientist to understand this. All we're saying here is that if you increase the frequency and you increase the wavelength both simultaneously, you should be able to travel faster in light. What physically prevents us from doing that? Why can't we travel faster in light if supposedly you can increase the mathematically, right? You can increase the frequency and the wavelength. So you make the wavelength longer, you make more, per unit time, and you have faster light. Very simple. Well, under the rope model, well, you can't do that. See, here's the rope model. If you have any length of rope, and here I have a piece of the rope here. The more I torque it, okay, the more links I have, and each link is smaller. So here we have frequency times wavelength. You untorque it, very simple. You have fewer links, and each link is longer. And then it gives you an idea why the speed of light is a constant, because it's mediated by a rope. Or at least it's a good, I'm not here to twist your arm, just saying, if you think about it, a rope is a good model for what we're seeing, for that equation. That equation is the equation of a rope. You cannot increase both frequency and wavelength, because you cannot increase on a given length of rope the frequency, how many links you have, and how long they are. You cannot do that. One is at the expense of the other, and that's what the equation shows. Okay, so this is what proposing in exchange for what mathematical physics proposes. Mathematical physics says that all particles are discrete. They have nothing to do with each other. They're separated by space. They're not connected. And the rope model that I'm proposing says that all atoms are interconnected. That's the bottom line. Okay, that's the fundamental difference between what we have today and what we have in the rope model. So how do we explain a slit experiment? We're saying that before we turn the light on, the ropes are already connected from atom to atom. All the atoms in this room are connected. Once we turn the light on, all we're doing is increasing the frequency, which means that, like here we're starting, there's no light at this point, it's just dark. Now we're going to turn the light on, and now we do produce a higher frequency. Now those same ropes are torquing at a faster rate. The atoms are pumping at a faster rate and torquing the rope at a faster rate. So suddenly you have this boom, 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 and so you go boom, 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 because you turn the light on. What does turn the light on mean? It means that you're going to give the atom a stimulus that forces it to pump faster. If it pumps faster, it's going to torque the rope at a faster rate. And what that translates into is shorter links and more links. Higher frequency, lower wavelength. Okay? And you see all these atoms connected to the screen, and each one is affected. Okay, so you're going to see all these rows pointing to different atoms on the screen, and each one is torquing at a faster pace. Then you say, well, why doesn't the whole screen light up? Why are there fringes? Why are there separations? So let's get into that. This is the explanation, the official explanation. They say when electromagnetic waves are in phase, you have constructive interference. Both waves are in phase. When they're out of phase, they cancel each other out. From a mathematical point of view, you see that at the bottom. When they're out of phase, they cancel each other out. But that's only a mathematical expression. It doesn't give you a why, what's the cause? First of all, there's no such thing as a wave, but even conceding that, why would they cancel each other out? With a rope, you can see that. First, we're just going to imitate. We're going to say, look, with the rope, we can do the same thing. If they're in phase, you have constructive interference. And when they're out of phase, you have destructive interference. Okay, now what is the physical cause of this under the rope model? You have the light coming from around the needle. You have only two ropes here just to show the mechanism. Maybe I can show this with my hands. You have this situation where you're moving like this, right? So you have a shift in the phase of each rope with respect to each other. And if you still remember what I showed you earlier, where you had fringes, where I verified fringes with a needle, you'll see that it doesn't go completely to dark. There's always a reddish color that fades out but then comes back in again. It doesn't completely die out. There's always some amount of red. It's not as dark as the background itself. Like if you look at the ceiling above where the laser was pointed, it's dark. And this is not completely dark. And again, what you're seeing is this situation. You're seeing something like this. Okay? That's what I'm showing there. Okay, and here you see from the person's eye, the ropes are coming from two sides of the needle, right there. One's coming from one side of the needle, the other one's from the other side of the needle, okay? So they come to an atom here. And right now, in this first one here, this is the case where lights are turned off. Nothing is on. You haven't yet turned the laser pointer on. These are the ropes that are connected simply from the needle to an atom on the screen. That's the screen atom there. And this is an atom in your eye, okay? Now I put it on this side because there was no other way, otherwise it would have been quite confusing to put it on that side, but you're really on this side looking at the screen. The screen is reflecting that light into your eye, okay? So even though I put the person over there, the person's really supposed to be on this side, okay? But I did that on purpose because otherwise it would have been a little too messy to show how the rope comes back, along the same, in the same direction from where the light went, okay? But just keep that in mind. These are the two ropes coming from each side of the needle. Here you have an atom on the screen. It's turned off. That's why it's black. And you don't see anything in that area because there's been no light shining. Okay? That's what I'm trying to show there. Second picture here. Now we're going to turn the light on. Okay? We turn the laser on. Light comes at a greater frequency. You can see the difference in frequency here. This has more links, and each link is shorter. And so now this thing is pumping to a wider area. You give it a stimulus. So now this atom was going pump, 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 and now suddenly it's going pop, 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 wider expansion of the atom and faster. Okay, and that triggers the signal to your eye. This is the atom in your eye. Receives that same signal. Just relays that same signal. Why do we have these dark bands? This one has the same number of links as this one, but they're out of phase. Like blue, it matches red. Red matches blue. They're out of phase by half a link. Maybe I can show it here better. If you have this situation where you have a blue one and a red one. Can you all see that? Okay. And we're going to pit that against a red one against the blue one. Okay. And what I'm saying is, even though they come from the same light source, they're out of phase by one link or half a link. And that's what's happening here. They're off by half a link. And so what happens? Suddenly you get a dark band in your eye. You say, well, why would that be so? Why does that happen? And we see that in the next image. You're seeing a blue strand of the rope and a red strand of the rope. They're coiled around each other. And you're looking at the rope head on. What you're seeing is this, right there. Okay, something like that. And that's what you're staring at. Now you can see that the one on the left, the upper left, they're both in phase. But the one on the right, they're out of phase. One is up, down, the other one is horizontal. I'm going to associate the two on the left, they're up and down, with a bright band, and I'm going to associate the one on the right, that's off by half a link, with a dark band. Okay? The guys on the bottom, both of them, you can see they're just at 45 degree. One of the ropes is 45 degree with respect to the other. And those are those intermediate colors that you will see. You'll see a phasing out, a fading out of the color, the red, because we typically use a red color. Okay. And so now we get to this, and here we have a dynamic version. This is what you would see if you're the atom. Okay, you have a rope coming towards you, right? And this is high frequency on the top, and you can see the atom is pumping, boom, 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 boom. That's what you're receiving. Why? Because both ropes that are meeting at your atom, they're both in phase. So the atom can expand through both ropes without any problem, no impediment. It just expands because they're both in phase, giving it the same signal simultaneously. What happens to the guy in the bottom? Well, now you have two superimposed. You have one rope that's like that, the other one that's sideways, okay? They're superimposed. Remember, they arrive at the same point. And so the atom's trying to expand here when the other one just gives it a different signal to expand in a different direction. So the atom is trying to expand like it did in the first guy, in the first case, trying to expand forward, eating two links, right? And it can't do that because one of the link is sideways. So it's trying to expand this way when the other guy says, no, expand that way. And so the atom is blocked from expanding to its full potential. That's what I'm saying is happening here. That's my explanation for it. Maybe there is a different interpretation. That's what I'm seeing that's happening if you explain this with a rule. So, ending, quantum mechanics has no physical interpretation for the slit experiment. First, because they use concepts such as field, force, etc., energy. You need objects to explain something. You should be able to put something on the board like I did here, some physical entities. Quantum mechanics cannot explain the slit experiment with waves because there is no such thing as a wave. Wave is what something does, not what something is. And the rope model of light, apparently at least, provides a physical interpretation for the slit experiment of why that happens. Okay? And that ends that second part of my presentation.